When you analyze a structure in STAAD, you may find these warnings reported in the output file. These are reported to inform the user that the structure is not stable or some zero stiffness conditions are present in the model. Do you know, for some specific conditions, this may lead to incorrect analysis and design result, or even complete failure of the structure? Hi, my name is Surajit Ghosh, and in this series, I will discuss about structural instability and zero stiffness condition, basic reason and technical background of instability, how to identify these problems in a model, what are the effects on the structure, and finally how to rectify the structure to eliminate these warnings. I strongly believe that it is better to understand the reason of instability first rather than just to know the tricks to rectify this problem. That's why I have included a basic discussion on structural instability in this session. Let's check the warnings. For zero stiffness condition, these warnings are reported. You can notice the direction of zero stiffness along with the relevant node number is mentioned here. Also, the equation number is reported, but that is not very important to understand the issue. In the first warning, probable reason of this condition is mentioned as member release, but it is not the only reason of zero stiffness. There are several other reasons which I will discuss using different models. If there are more than 12 such warnings, then program reports the first 12 and rest of the warnings are not reported in the output. But another warning is reported which indicates there are more such issues which are not reported. So we should review the entire model and eliminate all the problems. And for instability condition, direction and node number is mentioned in the warning along with the stiffness matrix information and equation number. Once again, this information are not our primary concern. Most important information is the direction of the instability and node number where the problem is occurred. For zero stiffness warning, the direction is specified as a number. Like in these warnings, the direction is mentioned as 3, 4, 5 and 6. Do you know what these numbers indicate or how to identify the problem using these numbers? Well, that's our first challenge. We need to interpret the warnings and correlate this to the model. For this, we need to first understand the concept of degrees of freedom. You can notice in the problem statistics, node number, member, and load information are reported. Along with that, an additional information is provided, which is the total degrees of freedom of the structure. To understand what is this number and how this is related to the stiffness warning, let's go through some basics. Degrees of freedom can be defined as all the possible displacement components of a node in space. So if you apply an external load on any node present in a 3D space, whatever is the movement or displaced condition of that node, we can define that as degrees of freedom. In classical mechanics, it is described as the number of independent parameters which define the state of a body in space. To understand this concept from structural point of view, let's take an example. Assume this is a free body of a node. This node can move and rotate in space in any direction. We can represent the movement of this node in space using three different axis system. So either the movement or displacement is along this axis or in a direction which can be resolved in this three axis system. Consider the horizontal axis as x, vertical axis as y, and axis perpendicular to this plane or out of plane axis as z-axis. Same axis orientation is followed in STAAD. If we consider the translational movement, this node can move along the x-axis, along vertical or y-axis, and also it can move in the out of plane or z-axis. For rotational movement, it can rotate about x-axis, it can rotate about y-axis, and also rotate about z-axis. So these are the 6 displacement components for any node, and we call this as 6 degrees of freedom. To summarize, there are all total 6 displacement components, 3 translational and 3 rotational, and each of these displacements are denoted with a number in STAAD. Translational displacement in x, y, and z axis are denoted with a number 1, 2, and 3. Similarly, rotational movement about x, y, and z axis, theta x, y, and z components are denoted with number 4, 5, and 6. In the zero stiffness warning message, the direction number actually refers to a particular degrees of freedom which you can correlate from here. For example, direction 4, 5, and 6 means the joint has no stiffness for 3 rotational components, or in other words, rotation about x, y, and z axis are not restricted. Whenever we encounter a warning message with zero stiffness, we need to understand the direction in which there is no stiffness and accordingly rectify the problem. Now, if we assign a support to a node, the free movement of the node is restricted in the supported direction. So, depending on the support condition, degrees of freedom change. For example, if we assign a pin support, we are allowing the rotation of the connecting member about x-axis, about y-axis, and about z-axis. The node or the connecting member can rotate about all 3 axes. Hence, 3 rotational components are present for this node. Translational movement along x-axis, along y-axis, and along z-axis are restricted for the pin support. This is just a representation to show the displacement components which are allowed and which are restricted. This is obviously not the actual displacement diagram, as the bottom portion of the member is not free to move. So, there will not be any displacement of the member at the support level. As a conclusion, for a pin supported node, the degrees of freedom reduce from 6 to 3. 3 rotational displacements are allowed and 3 translational displacements are restricted. And this is how the total degrees of freedom is calculated for any model, depending on the overall joint number, number of supported nodes, and support condition. For example, consider this frame model. There are all total 12 nodes, among which 6 are supported nodes, 4 are fixed support, and 2 are pin support. Now, if we calculate the total degrees of freedom without any support, then for 12 nodes with 6 degrees of freedom at each node, it is 72. For 4 fixed support, all the translational and rotational movements are restricted, and for 2 pin supports, 3 rotational displacements are allowed, and rest of the translational displacements are restricted. So, we can deduct those restricted directions from the actual degrees of freedom. The total number comes as 42. Same value is reported in the output as the total degrees of freedom of the structure. Now we need to understand the relation between degrees of freedom and zero stiffness problem. When STAAD analyzes a structure, it follows stiffness method to calculate the unknown displacement values. For stiffness method, which is also known as displacement method, this basic relation is followed. Load vector P equals to the stiffness matrix K into the displacement vector delta. For any statically determinate or indeterminate structure, STAAD forms the load vector and stiffness matrix and then performs the matrix inversion to calculate the unknown displacement components. In the analysis dialog, you can notice few statements like processing load vector or stiffness matrix, which indicates the analysis process using stiffness method. There are several methods for matrix inversion. In older version of STAAD, there were two different solvers based on selected license, basic and advanced solver. For advanced solver, modified Cholesky decomposition method is used for matrix inversion, whereas for basic solver, triangular factorization method is used, which is much slower than the advanced solver. That's why for a large model, you can notice a difference in analysis time between the basic and advanced solver. Basic solver takes considerable more amount of time to complete the analysis. Do you know, starting from Connect Edition Update 4, Basic Solver is discontinued and Advanced Solver is used with the basic license. Now, STAAD has only one solver, and if you analyze your model using any recent STAAD version, Advanced Solver will be used no matter what license is activated. If you use the latest version with basic license, you can experience a faster analysis due to 64-bit advanced solver, and I think this is one of the great advantages of Connect Edition. You should try this. Anyway, during analysis, when program assembles the stiffness matrix, it expects non-zero stiffness components in all 6 directions. During this process, if program finds that in a particular direction, whether that is translational or rotational direction, there is no stiffness, then a warning message is reported in the output for that node and for that direction. So, zero stiffness is nothing but absence of stiffness in a particular direction. There are several reasons for this condition, which I will discuss in detail. If there is no stiffness in a particular direction, then any load applied or distributed at that direction will not be transferred to the support due to no load path. Hence, the load will be lost. That is our basic principle of structural analysis, right? Any load applied on any part of the structure will travel through the load path and finally ends up in the support. Now, if there is no stiffness somewhere in the structure, which is a part of a load path, then that load will not be transferred to the connecting member. This creates an unstable condition which might be critical for structural integrity. Let's check this in a STAAD model. This is a truss model, very common one. You can find this type of steel truss in any industrial set or warehouse type of building. All the members present in the top tube are specified as truss. So these members can carry only axial load. No bending, shear or torsional resistance is present. After analysis, we can notice that there are 13 warning messages reported in the output related to the zero stiffness condition. There are 12 warnings for zero stiffness condition. Each direction and node number are reported here, and another message which indicates that there are more. These nodes and directions are not the only problem. there are several other which are not reported. If we check this message, we can notice that these are related to node number 16, 17 and 18, and the problem is in direction 3 to 6. As per our discussion, 3 means the translational displacement in z-axis and 4, 5, 6 are the rotational components. So for these nodes, there is no rotational stiffness in any direction and no stiffness in the z-axis. Let's investigate the reason for node number 16 and 17. All the members connected to node 16 and 17 are truss members. These members have only axial stiffness. That means they can carry and transfer only axial force. If we look at the member orientation at any of these nodes, we can find that this joint has stiffness only in x and y direction. As all the members connected to this node are truss members which can't carry any shear, torsion or bending, so there is no stiffness in z direction and also no rotational stiffness in any axis. That's why the warning messages are reported in the output, as in these 4 directions there is no stiffness. If any of this member is a non-truss member, then this condition does not occur, as that member contributes stiffness in all 6 directions. So for this model, the reason of warning is the member truss specification. All the members connected at a node are declared as a truss member. Let's check another model. This is a simple frame model. This type of frame is common in any building structure, whether concrete or steel. In this model, no member is declared as a truss member, but a member release specification is assigned to all these members connected at a common node. Analyze the model. There are 3 warning messages. Open the output file. 3 zero stiffness warnings are reported at node 14. Direction is 4, 5 and 6. All rotational direction, which means at node 14 there is no stiffness to resist the rotation about any axis. To find the reason, we need to check the details of this release specification. A full moment release is assigned about x, y and z axis. Mx, My and Mz moments are released, and this specification is assigned to all the members connected at node 14 and at the common member end. This means that there is no rotational stiffness present in any of these members at this joint. If an external moment is applied at this node, no member can resist that moment, correct? For this model, full moment release to all the members connected at a node is the reason of the zero stiffness condition. Nobody likes warning. If you submit this file to the consultant or reviewer, they will probably inform you to remove these warnings. Now, zero stiffness warning does not always indicate there is a problem in the model or the results are incorrect. It is just a warning to inform the user that there are some nodes which don't have any stiffness in a direction. Depending on the loading and other conditions, this might be harmless. Let's check the first model. We know that there are several zero stiffness warnings reported for this model, but does this mean it is unstable? In this model, I have applied 2 loads. Under load case 1, self weight is assigned to entire structure, and under load case 2, nodal load in z direction is applied. You may consider this as a wind load case. We have already discussed that due to absence of stiffness, load from that node cannot be distributed and it is actually lost. We can check this from the post-processing window, whether the applied load is distributed properly or not. In the post-processing mode, reaction page, under statics check table, the applied load and reactions are reported. For load case 1, the total applied load and reaction load match. For load in Y and moment about Z direction, so there is no loss of load, means zero stiffness condition has no effect on this load case. The reason is this is a gravity load and no load is applied in the zero stiffness direction. Though the warning message is reported, still for gravity load or any load which is not in the zero stiffness direction, we can ignore these warnings. For load case 2, the applied load is not equal to the reaction. See the difference? This means whatever load is applied on the structure, that is not transferred to the support. The reason is there is no stiffness at the truss level in Z direction and load is applied in this zero stiffness direction. So, no load path exists for this out of plane load. Hence, the load is lost. This is a serious issue as the total applied load is not considered in the support reaction and we need to rectify this model so that all the loads are considered and transferred to the support. Also, we can check the same information from the output file. We can include the print statics check command after analysis command, and once the analysis is over, in the output file for each primary load case, the applied load and reaction values are reported. Here also we can notice there is a difference in applied load and reaction load. For load case 2, applied load does not match with the reaction values. And not only the difference in reaction values, but there is also some other significant effect on the structural behavior due to this zero stiffness condition, that is large deflection. We know for load case 1, the warnings are harmless. Applied load and reaction values match. Check the deflection for load case 1. All 6 displacement components are within allowable limit, right? Next, check the deflection values for load case 2. 466 mm deflection is reported in the Z direction. See the deflection diagram for this load case. The deflected members are out of screen. As there is no stiffness in the Z direction, due to the applied nodal load in Z, the deflection is almost half a meter. This is not acceptable for any structure. For this load, zero stiffness condition not only causes load mismatch, but also a large deflection value is occurred. This model is structurally unstable and must be rectified. How to do that one? In next part, I will discuss about structural instability and cover few more details on zero stiffness condition. Stay tuned for more updates.